I'm going to be speaking about uniform manifold approximation and projection, or UMAP, and it's a dimension reduction technique that is founded in topological theory and has found a diverse variety of applications. So I'm going to look at both the theory and the practice of this. First of all, just a quick who am I? I'm Leland McInnes. I'm a researcher at the Tutte Institute for Mathematics and Computing. I'm also a maintainer for a variety of machine learning packages, UMAP Learn, HDBScan, Pioneer and Descent, and others. I'm also a contributor to scikit-learn and scikit-TDA. Okay, so let's just get ourselves started with the basics. What even is dimension reduction? So the goal of dimension reduction is to find some latent or hidden features in your data. And feature engineering is important. Visualization matters, and often a lot of the dimensionality in your data is, to be honest, completely redundant. So removing that redundancy in the dimensionality can help other machine learning algorithms. So let's take a quick look at a couple of data sets we might end up revisiting later. The first one is MNIST digits. This is the first 100 digits of a total of 70,000 samples from MNIST digits, and they're each 28 by 28 pixel images of handwritten digits. Each pixel is a dimension, so that's 784 dimensions. And surely you would imagine if we want to represent handwritten digits, we don't actually need 784 dimensions. Some much smaller number is going to suffice. Another example is fashion MNIST. It's a very similar data set, again, 28 by 28 pixel images, this time a little more complicated. It's fashion items, so shirts, dresses, shoes, bags, things like that. And again, we probably don't need 784 dimensions to sort of adequately describe or display such things. We might need a bit more than we need for handwritten digits, but certainly not 784. Okay, so this is all very well, but what is dimension reduction used for in practice? Well, a major use case is actually just visualization and exploration. So if you can do dimension reduction, particularly to 2 or 3 dimensions, it can make a very complex multidimensional data set visualizable for someone in just standard 2D or 3D plotting software. And one should never underestimate the value of being able to look at your data. Just visualization and exploration of a data set is a major use case for UMAP. So let's have a look at a few specific examples of use cases that have come up. So an interesting one is looking at genotyping the SARS-CoV-2 virus to understand different variants as they arise. And obviously, this is a pretty common concern and problem right now. But UMAP has been used in this, just looking at the genotypes and mapping them out to see how the variations differ from each other. It's also been used in actual COVID research, looking at how the effects actually apply to a human in COVID infections. But maybe in some less pressing examples, it's been used very successfully just for exploring how a deep neural network actually works, looking at how the activations in a large, complex convolutional neural network fit together. You can take the complex multidimensional space of the activations of a neural network and compress it into 2 dimensions, giving you something you can explore to get an understanding rather than having to just guess at what the black box is doing. But a different example again, here's our open syllabus galaxy. It's visualizing over 1 million textbooks based on the university syllabi they're listed in. And the results is a giant map. And you can zoom in and pan around and get a better understanding of what's going on amongst different textbooks, find associated things. It's a great way of just exploring the space of textbooks. But the other task that dimension reduction often gets put to is downstream processing. It's a pre-processing step as part of a machine learning pipeline looking to perform some other task. So a few examples, looking at birdsong and how it compares to human speech, using UMAP as a pre-processing step allows you to provide really quite useful clustering of the syllables in birdsong and how they structure together. And it shows a lot of similarities to how human speech syllables structure together to create words. So there, it's useful in highlighting some of these things. It's been used in astronomy for classifying objects such as galaxies, quasars, and stars, especially here working with really, really large data. This was a 111 million point data set. So it scales up as well. And as a final example, it's actually quite useful in natural language processing, such as topic modeling. There's a package called top2vec. There's another one called burtopic that both make use of UMAP as an intermediary step to get good clusters to refine and build topics out of. Okay, so clearly dimension reduction is useful. And I said at the start that the theory is based on topology, which is, relatively speaking, fairly abstract and obscure mathematics for something practical like machine learning. So the question is, why is topology relevant to this question? So let's explain classical machine learning and compare it to programming, and then we'll slowly build this around and see why topology makes sense for the sort of problems I'm trying to tackle. So one way to think about this is that classical programming works pretty simply. You have some data and some rules that you've gathered by, say, requirements gathering, and you're going to use programming to encode those rules so that you can shove in data and get results out. Machine learning, classical machine learning, supervised machine learning, the goal is to turn that on its head. What you have is some data and the results you'd like to get out given that data, and you shove that into the machine learning system, and it spits out essentially the rules for how to turn data into those results. But dimension reduction doesn't fall into the world of classical supervised machine learning. We don't actually get a set of results that we expect out. What we have is just an unsupervised learning problem where we get handed data and we somehow have to produce results of some kind. What sort of results? Well, if we're talking unsupervised learning, all we can really output is something about the structure of the data. So that might be cluster structure from clustering, density structure from a density estimation technique, or lower dimensional representations from dimension reduction. So with no labels or rules to guide things, what's going to determine any structure is how individual samples from your data set compare to each other. So what makes two samples similar and what makes them different? So ultimately, dissimilarity is the thing that's going to matter, and it looks a lot like a metric. It may lack some, or to be honest, even all of the properties of a metric in the strict mathematical sense. But various relaxations of classical metric spaces are very much the flavor of what's going on here. In other words, what we care about for unsupervised learning is geometry and ways to compactly summarize and describe that geometry. So we also have to be willing to accept the fact that we might not be getting a nice, perfect metric. So we're going to have to be able to cope with geometry in a flexible way. And this is almost exactly what topology is all about. So let's talk about topology and how it might apply to database tasks like dimension reduction. First, what is topology? Well, let's actually go to the Oxford English Dictionary rather than strict mathematical definitions. We care about both the definitions listed here. The mathematical one from the dictionary is the basis for the strict mathematical definition we're going to care about. It's a more general structure than classical metric spaces. But the latter one, that we're just looking at constituent parts and how they're interrelated and arranged, that we also really care about too. It's the interrelationships and arrangement of the data samples that we want to care about. So what we care about here really is the relative interrelationships between points. Exact distances aren't important. So this cute little cow is equivalent to its spherical representation from a topological point of view. We've retained the relative interrelationships. As long as we can continuously deform from one to the other, everything's fine. But that sort of view of topology makes heavy use of the continuum, infinite sets, and working with infinite sets requires a lot of care. Now, to be honest, I'm prone to making errors, so I prefer something nice and simple where I don't have to deal with infinite things. Also, in general, I don't have an infinite amount of data to work with, so I have to do something a little more finite. So how would you go about reducing topology to something that's finite and combinatorial? Just a bunch of key marker points, and maybe you could designate continuous spans among them in some way without actually having to deal with the infinity between them. And this is where simplicial complexes come in. And this is a basic tool in topology to do exactly what I described. So what we're going to do is build things up purely combinatorially, and then once we have the pieces, glue them together. So here's a one simplex. So this is defined as a one-dimensional span between two zero simplexes, which are just points. But the important point is we don't actually need to keep track of the detail of that continuous span. We can just represent it as the set of zero simplices that it happens to span. So it's just a finite set. We can define a two simplex as the span of three zero simplices bounded by one simplices. And a three simplex is a span of four zero simplices bounded by two simplices, and so on. But again, we're representing each not by the actual continuous span, but just by the very finite set of zero simplices that define that span. Now, if we start with some arbitrary set of points, let's just call them zero simplices, we can choose particular pairs and define one simplices between them, and particular triples and define two simplices spanning them, as long as we've already got the one simplices that bound it, and so on. And in this way, we can build up more complicated shapes and structures. And in fact, a vast swath of all topological spaces can be constructed up to topological equivalence in exactly this way. And the topological spaces that can't, well, they're mostly strange pathological spaces that we want to avoid anyway for the purposes of doing data analysis. And in general, all we're doing to make these spaces was just picking different subsets of the set of zero simplices and declaring them to be simplices as well. It's purely combinatorial. There's no geometry required. I want to step a little further into this than perhaps we really need, because it'll help outline why I think this is a powerful way of thinking about things. And this is the ability to move between different viewpoints. So let's define face maps. So for n simplices, there are n+1 associated face maps mapping to lower dimensional simplices. The ith face map simply leaves out the ith zero simplex from our set, giving a simplex one dimension smaller. So here we have the faces of a one simplex. We either leave out the blue point or the red point to end up with just a zero simplex. Likewise, we can play the same game with the faces of a two simplex. You can leave out one of the zero simplices and we're left just with the one simplex that's the opposite face. So all this generalizes, especially if you're thinking of simplices in terms of sets and combinatorics instead of geometry. But we can flip all of this around. We can take the simplices themselves as primitive objects, not as sets of zero simplices, just objects in themselves. And then as long as we're granted the face maps, we have all the data required to glue them together into a simplicial complex. So thinking of this in an algebraic categorical way, sort of category theory, we can look at it differently. We can think of sets of zero simplices. X0 is the set of all the zero simplices. X1 is the set of all the one simplices. And I'm not going to say which zero simplices make up each one simplex. I'm just going to declare there's a set, and each of those objects in that set is a one simplex. And then X2 is the set of all two simplices, and so on. And as long as I have the face maps, all those arrows mapping between them, the arrows are what are defining this simplicial complex and gluing everything together. So we started with geometry, and then we translated that into combinatorics. And then we translated that into something that's much more classical algebra or category theory for how we want to think about it. And I actually believe this kind of mental shifting of view is both very powerful and very important. So if you're looking for reasons to learn category theory, then this should be the motivation, because it's this kind of translation between different points of view that all ultimately describe the same thing that category theory provides. And importantly, when you start with a problem that's hard in one view, you can often shift to another and suddenly it becomes much, much simpler. Okay, let's talk about applying simplicial complexes to data. How can we do that? At least one way is via what are known as Cech complexes. And these are actually pretty general, but I'm going to describe them here from a very data-centric point of view. So suppose we have some data and a notion of dissimilarity between the samples. So here I'm just going to use Euclidean two-dimensional space. So the similarity is what you see. What we're going to do is put a bunch of balls about each sample of some fixed range of similarity. And these balls are going to cover our data set. Whenever two such balls intersect, we're going to create a one simplex between the data samples. And whenever the balls are very small, this doesn't really do much. We don't see anything. But once we get a little larger, we can make more intersections and we'll get more simplices. And whenever we get a triple intersection of balls, we'll add a two simplex in. Whenever we get a quadruple intersection, we're going to add a three simplex and so on. This is the Cech complex construction. As we make the balls larger and larger, we're going to get more and more complicated and higher dimensional simplicial complexes forming until we reach a point where we really have captured a lot of the topological structure of the data quite successfully. So this is a relatively effective proof by picture, but you should be wary because pictures and toy data sets are often very deceiving. What we do have, however, is a theorem from topology. So for our purposes, just so we don't have to go into details, take this as a picture of a theorem. It just says that whenever we have a good cover of a topological space, then the Cech complex we form, called the nerve of that cover, will actually be equivalent, up to some topological fudging, to the original space we started with. So what the theorem tells us is that extracting the Cech complex from data samples will preserve the topological information of the underlying space the data was actually sampled from. All right, now that we've got some preliminaries out of the way, let's look at how UMAP actually works to perform dimension reduction. Let's take some points, and I've color-coded them by their position along a sinusoidal manifold here. Now, the samples were noisily drawn from this underlying space. That's the sine wave. And topologically, that's just going to be a line that we're going to end up straightening out. But what we'd like to do is recover that. So we can build a cover by placing open balls of some radius on each point. And then we can build the Cech complex. But we didn't get what we wanted. Why not? Turns out our cover wasn't good in the way that we really needed it to be. It didn't actually cover the space, it only covered the points. There were gaps in the cover that didn't overlap parts of the underlying space, and other regions where the cover clumped up too much, and we got very high dimensional simplices. So here you can see there are gaps between some of the teal colored balls where we know the underlying manifold kind of spans between them, but the cover doesn't cover that region. And likewise, down in the lime green region in the bottom right there, the balls are overlapping far too much. So we can't get a consistent size of ball that's going to work everywhere. So the catch was in the distribution of the data. We didn't cover some parts of the manifold because the points were too sparse there. We also have clumps because the points are too dense there. If the points were uniformly distributed on the manifold, then this approach would work. Great. Here's the same manifold now with points uniformly distributed across it, and we can just drop our balls down of a nice fixed radius, and everything is going to work perfectly. You can imagine the Cech complex that would construct. It would look exactly like what we would imagine. But the catch is that data is never that nicely behaved in practice. So let's just make an assumption. Let's just say that the data is uniformly distributed on a manifold that we care about. The catch is that this has implications for the manifold. For the data to be uniformly distributed, we need a notion of distance on the manifold that varies and isn't simply inherited from the ambient space. So if we think of manifolds as locally Euclidean, different patches mapping to Euclidean space in different ways, according to the metric or the measure of distance, we can vary that across the manifold, and we can exploit that to estimate different local metrics for each data point. So we're going to map to a slightly different scaled Euclidean space around each data point, so that the data looks uniform with respect to that varying notion of distance. And another assumption that's going to creep in here is that the data is locally connected. The manifold is locally connected. And this avoids a lot of those nasty pathological spaces, topological spaces that I talked about, that aren't modeled well by simplicial complexes. All right. What we're going to end up with is a cover that's going to look something more like this. We're going to be confident out to the first neighbor so that we're locally connected. And then we're going to be fuzzy in our confidence after that, as our confidence in that local metric defined around each point declines. Of course, there's still a glaring problem that we've been ignoring, and that's that the approximated different notions of distance for each point are going to be different and incompatible. There's no reason to assume they have to match up with each other, and in practice, they almost never do. But again, the background theory comes to the rescue. Again, just think of a picture of a theorem. It's not worth worrying about the technical details here. But this is really just a simple adjustment of a classical theorem in algebraic topology. And it says that we can translate back and forth between the kind of local metric spaces we have and something called fuzzy simplicial sets. And this is essentially the same as simplicial complexes, bar some technical details, where each simplex is going to end up with a probability of existing. And this is the kind of change in viewpoint that I discussed earlier. We're flipping from the very geometric approach to something that's now very category theory and algebraic. But in that viewpoint, it's very easy to glue all these things together. There's a natural approach. You can just take colimits. It's the natural thing to do from a category theory point of view. And it glues everything together, and we end up with a single fuzzy simplicial set as a result, and everything works itself out in a very clean way. So this changing of viewpoints was kind of a key way to just adapt, change to somewhere where it's easy to solve the problem instead of being a tricky one where we're having to make arbitrary choices. The end result is a weighted simplicial complex, but equally importantly, the theoretical justification for why we constructed this particular graph with the decisions made by the underlying theory rather than sort of somewhat arbitrarily. And now we need to somehow get that to a low dimensional representation. So let's suppose for a moment that we were handed a low dimensional representation of the data. How could we tell if it was a good one or not? We'd need a way to compare it to the original one. So we could apply the same process I just described and get a simplicial complex for the low dimensional representation, and then measure the distance between the complexes using fuzzy set cross entropy. So that's going to have a formula that looks something like this. And the key part here is that when edges have a high probability of existing, the left-hand term, we want the ratio of existence probabilities to be 1. While for very low probabilities of having an edge, we want the relative comparison between the probability of not existing to match up. So the real trick is that now we can measure how good the low dimensional representation is. We can potentially see how to improve the representation. So what we're really doing is kind of a low dimensional graph layout algorithm. The left-hand term from the cross entropy is going to pull points with a high probability of a simplex existing close together in the representation, and the right-hand term is going to say we need to move those points that with a low probability of simplex between them further apart. And we're just going to move points around in the representation accordingly, so we can get a better and better low dimensional representation. So this is now just an optimization algorithm to steadily improve the low dimensional representation. So even if we start with a bad low dimensional representation, like say a random one or one based on the Laplacian of the graph, we can steadily improve it until we do get a good one. And so from a theoretical point of view, this is the algorithm. Try to match the topological representation between the original data and the low dimensional representation of the data. How do we go about this? in practice, however. The theory sounded nice, but all of this actually has to run on a computer in a reasonable amount of time. How do we turn math into workable code? So from my own point of view, I like to start by thinking about data structures. The math usually has a lot of abstract concepts, and it helps a lot to determine what they're actually going to concretely look like when represented on a computer for efficient implementation. A lot of the rest of the problems start to get a lot easier once those decisions are made. So the fundamental objects are these fuzzy simplicial complexes, and we need concrete representations of these. Once we have a good way to represent these on the computer, figuring out the rest of it is going to be a lot easier. So while the simplicial complexes are often described in terms of sets, we'll be a lot better off from a computational point of view if we can use just nice n-dimensional arrays instead. So to get an array of dimension n+1, we can represent n simplices in those. So 0 simplices are a one-dimensional array, just a vector. 1 simplices get a two-dimensional array, 2 simplices get a three-dimensional array, and so on. And what we're going to do is that the membership strength of simplices as a fuzzy set, the probability of the simplex existing, is going to be the corresponding entry in the array as needed. So we're going to be indexing according to the array of 0 simplices. So as long as we keep that consistent indexing among all the arrays, we have all the information to assemble the simplicial complex. The catch is that we're going to need as many arrays as the dimensionality of the highest dimensional simplex in the complex, +1. And hint, we're probably going to want to truncate that off at some dimensionality to make it more tractable. In practice, I tend to truncate off at just the one-dimensional simplices. That's enough to make the algorithm workable. And one thing that helps us make this workable is that most of the entries are going to be 0. The simplices in question don't exist, or at least have a sufficiently low probability of existing that we can truncate them away to 0 to make representation on computer easier. So that means we get to use sparse data structures. So one form of sparse representation is coordinate format or COO format. It effectively just keeps a list of all the tuples that are non-zero and a list of the corresponding values in that entry. And note that this is pretty much exactly the set of simplices style approach we were first thinking of, but it provides a more classical computer-oriented view of the same thing. So I said we were going to truncate down to just the one simplices. If we do that, then we can use actually sparse matrices, which are well studied. So COO format is very good, but there are also a lot of other formats for representing sparse matrices, such as the compact sparse row format, which is very, very efficient. There's also lots of libraries for handling all of this efficiently, so you don't have to code it all yourself from scratch. All right, having gotten core data structures now nailed down, the next question is, what algorithms do we actually need as the sort of pieces to put together? Construction of the simplicial complexes and sparse matrices is mostly just a matter of chasing the formulas through and doing the computations, but there are going to be other aspects of this that are going to be tricky. So since we can compute gradients of that cross entropy loss and even chase it back through the graph construction computations, we can use gradient descent type algorithms for that optimization step. So essentially, we're just going to create an optimization landscape and follow the gradient down to do a better solution. The catch is that this is really going to be order n squared, because we potentially have up to n squared neighbors, which is really not useful on most data science applications, where you're going to have thousands or even millions of samples. So at this point, we need to look at shortcuts. And one shortcut is to just truncate away those low probability edges, take our sparse matrix as we had. And in that case, we only need to find the nearest neighbors of each point. And the remaining optimization, that's still going to be hard, but that means we have two problems. Two hard algorithmic pieces that we're going to have to solve. And that's going to be finding the nearest neighbors, which actually is a surprisingly challenging problem in high-dimensional spaces, and the optimization of that low-dimensional embedding. At this point, I start doing literature surveys through all the styles of problems for how to go about doing this and what the state-of-the-art solutions actually are, and then just borrow ideas. So the solutions I arrived at was nearest neighbor descent as an efficient algorithm for constructing approximate nearest neighbor graphs for a data set, and just classical stochastic gradient descent with negative sampling for the optimization. So quickly, let's look through what nearest neighbor descent does. Is you can think of it as searching through a graph to move toward a query point. So we're just running a search for the nearest neighbors by literally walking through a graph. Okay, that assumed we had a graph. But if we start with a graph that's maybe not a very good nearest neighbor graph, we can essentially run one step of that search and find a slightly better graph, and then use that graph for another step of search, and so on. So even if we start with a random graph, we can iteratively improve the nearest neighbors as we go and get a better and better graph, bootstrapping ourselves up to a good nearest neighbor graph. This is going to be approximate, but it'll be good enough for most purposes. And stochastic gradient descent with negative sampling was actually most famously used in the word-to-vec algorithm. And it can be helpful to see the solution in that context. So word-to-vec has a very similar push-pull algorithm going on. Words are pulled towards more similar words and pushed away from dissimilar words. And instead of computing the gradient for a given word, we're going to do it piecemeal with individual interactions. That's the stochastic part. So consider, for example, that there might be a small list of words that are similar to a given word. We take the word topology, maybe similar words are geometry, shape, mathematics. What are the dissimilar words? Well, almost any word is dissimilar in some way. So finding and looping over all the dissimilar words is going to be far too expensive. So instead, we just randomly sample a bunch of words and take those as our negative examples. And the expectation is that since most words are dissimilar to each other, we can select them entirely at random. Obviously, we aren't covering all the possible dissimilar words in this way, but if we select randomly each time and iterate enough, we can still do remarkably well. So we also have to consider what this is going to look like for the algorithm. So this is a thing that I spend a lot of time considering that maybe is less common among academics, but I actually care about the APIs. I want to have it used by as many users as possible. And if you want to get your algorithm used, you need to make it as easy to use as possible for as wide an audience as possible. And my solution to that is to let somebody else do the hard work for me. So most people in machine learning these days are familiar with a package called scikit-learn. And it's pretty ubiquitous. So by simply following their API for how to use it and make it slot into all their standard tool chains, the implementation I write becomes immediately accessible to a very broad range of users. They can use UMAP instantly as a drop-in replacement for all their existing dimensionality reduction techniques that were implemented in scikit-learn. So on to very practical end of things, the implementation side. I noted that I want to go where the users are. So for machine learning these days, that means Python. And a sad thing about Python is it's not very fast. But there's a great library called Number, which actually takes numerical Python code and compiles it down to LLVM machine code. So what this means is you can actually program in Python and have it run at pretty much the same speed as what you get if you are coding in C. So this is very worthwhile. So as a performance comparison, compared with TSNE, well, there are, I will say, some more state-of-the-art TSNE implementations since I made up this chart that are much more comparable to UMAP, but this gives you an idea of the kind of speed-ups that were in place. And TSNE, and this implementation that I'm comparing to here, was a C++ implementation. And so UMAP, even coded in Python, is running significantly faster. A lot of that comes from the stochastic gradient descent. TSNE can't use stochastic gradient descent because it can't separate all the terms in the low dimensional representation. It has a global normalization constant, and the nearest neighbor search is made much more efficient. Okay, so how does it actually perform on data? Well, here's the MNIST digits data set that we saw at the start. And this is a two-dimensional representation using UMAP. Each dot represents a handwritten digit, and they've been color-coded by the numeric value of the digit they represent. And this is remarkably good. The ones are on the far left, the zeros are on the far right, and there are groups of digits that you might expect look kind of similar in some ways. The 4, 7, and 9 up high group together, the 8, 5, and 3 in the middle tend to group together. So we're getting structures that we would expect. This has some of the properties of TSNE. It's managed to pull everything into clusters very cleanly, but also some of the high-level structures have come together very nicely that you might expect from something more like PCA. We're trying to balance between the two, and it's a hard balance to strike, but this is at least one path along that line. And here's fashion MNIST. It's not as good. The data set is more tricky. We're compressing it into only 2 dimensions. We expect that to be very hard. But we're still picking out most of the classes, and a lot of the structure we care about on a bigger picture scale makes sense too. The pants or trousers are well separated away, and the 3 different classes of footwear are all together and distinctly separate from everything else. But there's actually more we can do still. It's not that hard to actually fold in label information with the existing theory, so we can do supervised dimension reduction. Here we have fashion MNIST embedded using label information. So now we neatly separate out all the classes, as one would expect. We told the algorithm what the class of each sample is, but we retain the internal structure that we saw in that previous plot within each class. So we're visualizing a lot more information here. We can also do all manner of different spaces to embed too. Remember, as long as we can build a fuzzy simplicial complex for the low dimensional space and apply gradient descent updates, we can apply the algorithm. So here we have embedding data onto a sphere, a torus, into hyperbolic space in the bottom right, and on the bottom left, an energy distance based space of Gaussian distributions. And so actually the last one is interesting because the sample is represented not as a point, but as a distribution in 2D. Thus, we not only have a position for the sample in the low dimensional representation, but also a measure of the uncertainty. A more recent addition has been parametric UMAP by Tim Sainberg. And here we're going to replace the simple stochastic gradient descent optimization with a neural network from the original space to the low dimensional representation using the same loss function. And this allows for some extremely fast inference on new data, since we just have to push it through this trained neural network, which means you can get results for new unseen data points in the same sort of time frame it would take you to do that with PCA, which is extremely fast. But there are also interesting games such as semi-supervised training of the networks. That is, we're going to train the neural network to predict the class of an MNIST digit from a small number of examples, but also to produce a UMAP low dimensional representation from the rest of the unlabeled data. And this can get some astonishing accuracy with only a handful of labeled examples. In this case, with MNIST digits, Tim was able to get up to 98% accuracy with just 4 labeled data points per class. So with only 4 labeled samples, as long as you have the rest of the data to learn the underlying structure with the UMAP, you can still get an incredibly powerful classifier. Only 4 labeled samples is, to be honest, quite stunning to me. And another recent addition is the ability to align multiple distinct UMAP embeddings, allowing for interesting time-based analysis. So in this picture here, we have embeddings of the representatives from the US House of Representatives over time. So each representative is a curve where each time slice is an embedding for a given year, and the embedding is determined by how they voted on all the votes that came up in the House of Representatives. So how they compare to other representatives. but we get to see how that varies over time by aligning each of the embeddings with each other. So you can see both the strong partisan divide, but also various factions and movements. And the notebooks to run this are all online if you want to try it out. And you can get an interactive 3D plot that you can scroll around and zoom in on. And there's yet more that can come after that. Hopefully you have some interesting ideas about new directions we could go. So thank you. And I guess I can take some questions.